Hello everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and discuss what it means for a set to be a null set and why we should care. So, what exactly is a null set? It's very important to not conflate the idea of a null set with the empty set. They are quite different. So, a set A, a subset of the reals, is said to be a null set if for any epsilon greater than 0, there exists a countable collection of open intervals ik. Those boundaries are ak and bk, and usually we would like these intervals to be non-empty. Some people include that specification here, but I'm not going to today. So, if k is an element of the natural numbers, then these intervals must satisfy a property for A to be a null set. First off, A must be a subset of the union of all of those open intervals, and the sum of the lengths of those intervals, which is bk minus ak, must be able to be made as small as desired. That's this epsilon greater than 0. So let's do a couple examples to sort of get an idea of what exactly a null set is. So the very first example is the empty set. Is this a null set? Indeed it is. So how are we going to prove that the empty set is a null set? So obviously we're going to be starting the same exact way as we usually do. Let epsilon be greater than 0. And let's choose our intervals to be equal to empty intervals, in particular ones of the form a to a, where a is any real number, your favorite real number that you like. For example, pi square root of 2, e, whatever you want, right? But they are open intervals, so life is good in terms of that choice, right? So these are indeed open. They're also closed, but they are open. That's the only thing we need here. So let's check the properties to make sure that they are satisfied. So the first property is that the set of interest is a subset of these. So we have the empty set is a subset from, so let's do the union from k is equal to 1 to infinity of our intervals. So that's just the empty set union with the empty set union with the empty set union with the empty set union and so on. That's obviously just the empty set. And regardless of what the set would be, the empty set's always a subset of that set anyway, so the first property is obviously true. Now let's make sure that these lengths can be made as arbitrarily small as possible. So the lengths of each of these intervals, so the sum from k is equal to 1 to infinity of the length of ik, well the sum of all of those intervals is just 0, so we're just going to have the sum from k is equal to 1 to infinity of 0. So we have, that's going to be 0 plus 0 plus 0 plus 0. We're never going to have any length, and that's going to be 0. So regardless of that epsilon value you've chosen, that's always less than epsilon. So that second property is satisfied. So since both of these properties are satisfied, we have, by definition, that the empty set is a null set, right? So at least from that example, you probably don't exactly know what a null set is and what distinguishes it from a null set, but the next example should enlighten you a little bit more, because this one, at least if you've never heard of a null set, is not very intuitive, and it says the following, that the set of integers also is a null set. So obviously we're covering a lot more space. We have infinitely many numbers now compared to 0 with the empty set, but this is also a null set as well. So how to prove? So we're going to let z be equal to x1, x2, x3, x4. That is, this is just some enumeration of z. Because we know that z is a countable set, so we can always create a enumeration with respect to the natural numbers such that this representation exists, right? So this is obviously a countable enumeration, but I'm focusing on these integers in some particular sequence, and that should be an infinite set, so I shouldn't have that totally closed off. Right? So I'm focusing on my numbers regardless of the order, so it could be 1, negative 1, 2, negative 2, 3, negative 3, 0, 4, negative 4, 5, negative 5, and so on. So I'm going to define these intervals and also choose any epsilon greater than 0 that you want, and we're going to let ik be equal to intervals that are centered around xk, where k ranges from 1 to m. And the radius of it is going to be chosen to be epsilon over 2k plus 1, epsilon over 2k plus 1. So what exactly am I doing here? So I'm looking at all of my integers, right? So here's my integers. Here's 0, here's -1, here's +1 or -1, doesn't really matter. -2, +2, and I'm just building intervals around them. So I'm building this interval, this interval, this interval, this interval, this interval, and each of them are dependent on epsilon. So regardless of that epsilon, I can always, that interval automatically becomes smaller. But keep in mind I have an infinite number of intervals, so the infinite sum of the lengths of these ik's must also be made arbitrarily small, right? So that's where the denominator, chosen to be 2 to the power of k plus 1, obviously is going to be some sort of geometric series, is going to be able to be made as small as I desire. So let's check the math just to make sure that this indeed works. So the first property is that z is a subset of the union from k is equal to 1 to infinity of these intervals. Obviously, since all of my integers are in the middle of each individual interval, we clearly see that z is a proper subset of the union of all of them, because we also have the region subtly to the left and subtly to the right of each of those integers as well, provided that epsilon is a positive number, which indeed it is chosen to be. So that property is trivially satisfied. So let's make sure that the length property is also satisfied. So we need to sum from k is equal to 1 to infinity the lengths of each of them. So the length of ik. So that's going to be equal to the sum from k is equal to 1 to infinity of, so bk is xk plus epsilon over root of 2k plus 1, and then minus xk minus epsilon over 2k plus 1. Notice regardless of the interval we're on, those xk's are going to cancel, and we're just left with the sum from k is equal to 1 to infinity of, and we have epsilon over 2k plus 1 minus negative epsilon over 2k plus 1. So we have 2 of those epsilons over 2k plus 1, and we know that that's going to be equal to the sum from k is equal to 1 to infinity, and epsilon is just a constant, so I can factor that out. So I'm going to have 1 over 2 to the power of k, and that's precisely a geometric series which obviously converges. So this is going to be equal to epsilon. Notice that my sum starts at 1 and not 0, so we're going to have 1/2 divided by 1 minus 1/2. And we have 1/2 over 1/2, which is 1, so that's equal to epsilon. And we know that epsilon is less than or equal to epsilon for any epsilon that is chosen. As long as epsilon is a positive number, we are safe. Therefore, the second property is satisfied. So since both of those properties are satisfied, then we have that z is a null set too. So even though there are points, they do not necessarily cover a large area because they're isolated points. So practically, this proof can be used for any countable set, because I didn't really specify those integers. I just created an enumeration x1, x2, x3, and so on. So following a same exact proof, you can prove the following wonderful theorem. And it says the following, that all countable sets are null sets, right? So this includes, for example, finite sets, the empty set, singleton sets, so singleton sets, unions of singleton sets, finite unions of singleton sets at least, the natural numbers, the integers, the rationals, and there's obviously several other countable sets out there. But this is definitely true and proven in practically the same exact manner. The next statement is a phrase that's commonly tied with null sets, and it's the phrase almost everywhere. So let's assume that px is a statement about x and a. For example, oh, this function is differentiable in this set, the function is continuous on this set, the function is Riemann integrable in this set, and so on. Then we say that p of x holds almost everywhere, sometimes abbreviated by AE, on the set E, if there exists a null set N with the null set a subset of A, so obviously it can be an empty set, such that P of x is true for all x in A except for null set. So the null set practically covers no space, no area at all. Therefore, since P of x is true for all x in the set A except for a practically empty or practically invisible set, then we say that P of x is true almost everywhere. Now, this leads into probably one of the more important theorems of basic real analysis. And this theorem is sometimes referred to as Lebesgue's integrability criterion. So Lebesgue's integrability criterion. And it says the following. So suppose that f, or let's define a is equal to the closed interval ab, and let's assume that f maps a to R, and let's assume that f is bounded on the set A. Then the function is Riemann integrable on A if and only if f is continuous on A almost everywhere, which you could also write that f is an element of the continuous functions on A almost everywhere. Right? So as long as the set of discontinuities forms a null set, including an empty set, then this theorem says that the function must be Riemann integrable. Keep in mind, this goes both ways. Right? So just a couple notes in terms of terminology, in case you haven't already figured it out. So notice that everywhere, if it's true everywhere, then that means it's true almost everywhere. But if it's true almost everywhere, that does not necessarily imply that it's true everywhere. So this is just a semantic language thing. So let's consider a couple functions that we've discussed throughout the series up to this point. The first, let's define the Riemann function to be equal to the sum from n is equal to 1 to infinity of 1 over n squared sine of n squared x. So we've already proven, using absolute convergence, for example, that the function is continuous on all of R, right? So that means the set of discontinuities, of Ri is the empty set, which obviously is a null set. So since the set of discontinuities is a null set, then we obviously see by Lebesgue's integrability criterion that the Riemann function is Riemann integrable on R. Okay, and it's very easy to see that this function is indeed bounded on R as well. So let's look at another example. Let's look at the Weierstrass function with parameters a, b, defined to be the sum from n is equal to 0 to infinity of a to the m cosine of b to the m pi x, where a is between 0 and 1, b is a positive integer that is odd, and the product of ab is strictly greater than 1 plus 3/2 of pi. Right? So if you don't remember anything about this function, a couple things you probably should know is that the Weierstrass function for these particulars a, b is continuous on all of R, but it's not differentiable anywhere on R. But that's okay, because the set of discontinuities for this set, since it's continuous everywhere, is again the empty set. So since the set of discontinuities is obviously a null set, that means we have that the Weierstrass function with parameters a, b is Riemann integrable on R, and obviously you should be able to show that this function is indeed bounded by some number, right? And that's of course provided that a is between 0 and 1. So let's look at a couple other functions as well. So example 3, let's consider the Thome function. So the Thome function, remember, is defined to be 0 if x is a irrational number, and it's defined to be 1 over b if x is equal to a over b, a rational number with the greatest common divisor of a and b being equal to 1, i.e. a and b are relatively prime. So what are the properties of the Thome function that we've proven before? So the Thome function was continuous on the irrationals, and the Thome function was not continuous or discontinuous on the rationals, right? So here are the issues. So the Thome function is discontinuous. So the Thome function is discontinuous on Q. And we already know that Q is a countable set, and we already know that all countable sets are null sets. So since the set of discontinuities for the Thome function is a null set, then of course we have that the Thome function is Riemann integrable on R. And of course you should be able to show that this sequence is indeed bounded, or this function is indeed bounded. Right? Let's look at another very important function, and that's the Dirichlet function. So the Dirichlet function, or the indicator on the set of rationals of x, and this is defined to be equal to 0, again, if x is irrational. And let's assume it's 1 if x is rational. Right? So one of the theorems and things that we proved about the Dirichlet function is that the Dirichlet function evaluated at x is not continuous on R for all x in R. Right? So that means the set of discontinuities, so the set of discontinuities for the Dirichlet function is R, and you should be able to show that R is not a null set, right? So since the set of discontinuities is not a null set, because keep in mind this is an if and only if statement, that means the Dirichlet function is not Riemann integrable on R, or any non-empty subset of it, right? So we can make a little table to sort of summarize these results. So we're trying to answer the questions of Riemann integrability, right? And this is due to Lebesgue's theorem. So we have the Riemann function, the Weierstrass function, the Thome function, and the Dirichlet function. And what was our conclusion for each of these four? So the Riemann function was Riemann integrable, the Weierstrass function was Riemann integrable, even though it's nowhere differentiable. The Thome function was, and the Dirichlet function is not. Right? So those things are very, very important, and some interesting counterexamples to sort of think about when it comes to Riemann integrability. But there's another character that I want to sort of discuss because it's very similar to a Dirichlet function, but it has a property that the Dirichlet function does not have. So let's take a look at that. Before we introduce our fifth function that we want to discuss in terms of its Riemann integrability, I need to first define a new set that you probably have not or probably have heard of. That's called the Cantor set. So the Cantor set is going to be defined recursively, and it's going to start off with a closed and bounded interval 0 to 1. So we're going to start off with all real numbers from 0 to 1, and what we're going to do is we're going to partition this into uniform subintervals, in particular 3 of them. That is, we're going to partition this into thirds. And what we're going to do is we're still going to include 1/3 and 2/3 into the set, but what we're going to do is we're going to remove everything from 1/3 to 2/3, right? So we're going to remove everything there. So what we're left with is what we're going to define as C1. So C1 is going to be equal to the closed interval 0 to 1/3 union 2/3 to 1. And that's going to give us a new interval. So obviously we have 0 to 1/3, and we also have 2/3 to 1 still remaining. Now, with these intervals, what we're going to do is we're going to partition them into thirds, and we're going to still keep those boundary points. So what is that? Keep in mind this is the same as 3/9, so this is going to be equal to 1/9 and 2/9, 3/9, 4/9, 5/9, 6/9 there, and then we're going to have 7/9 and 8/9 there. And then what we're going to do is we're going to take these middle thirds of those intervals and remove them. So once we remove them, then what are we going to have for C2? So C2 will be equal to 0 to 1/9 union 2/9 to 3/9. So that's the left two intervals, and then we're going to have 6/9 to 7/9 union from 8/9 to 9/9, which is of course 1. right? So how many intervals do we have on each iteration? So obviously we have 2 to the 0, 2 to the first, 2 to the second, and so on. So you should be able to see or verify, at least by mathematical induction, that Cn will contain a union of 2 to the power of n closed intervals, right? And also, what are going to be those lengths? Those lengths are going to be equal to, so notice we go from 1 to 1/3 to 1/9, which is obviously just 1/3 the quantity squared, right? So each of these lengths are going to be equal to 1/3 to the power of n. So for C3, each of those are going to be of length 27, 1/27. So what we're going to do is we're going to take the limit of these things and we're going to define a new set, which I'm going to call CA, to be equal to the limit of Cn. And this set is what I'm going to refer to as the Cantor set. Okay, so what exactly does the Cantor set contain? Well, obviously the Cantor set is going to contain a set of points. It's obviously not going to be empty because it's always going to contain 0 to 1. So that's after the 0th iteration. After the first iteration, it's obviously trivial to see that 1/3 and 2/3 are going to belong to that set. After the second iteration, it should be obvious to see that 1/9, 2/9, 7/9, and 8/9, the boundaries of those intervals are also in that set, and so on. So we clearly see that the Cantor set is not empty. A couple other properties that you should be able to see are the following. For example, C0 is entirely covering C1, that is C1 is a subset of C0. Obviously, C2 is a subset of C1, C3 is a subset of C2, and so on. So you should be able to verify from this nested interval that the Cantor set is just simply the intersection from k is equal to 1 to infinity of ck, right? And what type of representation of the Cantor set is this? Well, obviously this is an intersection, an arbitrary intersection, or more so a countable intersection of closed sets, because each of these CKs are indeed closed because it's a finite union of closed intervals, right? So those are indeed closed. So since we have an intersection, a countable intersection of closed sets, that means that CA also is a closed set. Okay? And you should be able to investigate several other properties as well for the Cantor set, and I'll list some of those important properties out. So let us assume that the Cantor set, obviously a subset of 0, 1, then the following properties are true. So the first property is the following, that 0, 1, take away the Cantor set, is actually a dense subset of 0, 1. And you should be able to easily verify this second statement, that the Cantor set is not a dense subset of 0, 1. That's actually very easy to prove, right? And maybe you can prove 1 as well. The third property that you definitely should know about the Cantor set is the Cantor set is not countable, but it's uncountable. And the fourth property that you definitely should know is that the Cantor set is a null set. And you might be able to see that because practically after we go over each iteration, all we're going to be left with is just the boundaries of those intervals, and those boundaries obviously are isolated points. So now we know a little bit about the Cantor function and some of its important properties. Let's define a new function, and let's call it the Cantor function. And let's define the Cantor function. Let's abbreviate it as CAN, and let's assume that CAN maps 0, 1 to R via the following definition. And we're going to define it similar to the Dirichlet function. So the Cantor function of x, which is obviously going to be the indicator function on the Cantor set, is going to be equal to, again, 0 if x does not belong to the Cantor set, and 1 if x does belong to the Cantor set. All right, so here's our Cantor function, and let's state a couple properties that are definitely maybe a challenge to prove on their own, but definitely not impossible. So one can show the Cantor function is discontinuous. It's discontinuous on the Cantor set, and it is continuous. It is continuous on its relative complement with respect to 0, 1. Okay? So if that is the case, then what exactly do we have? So the Cantor function has a set of discontinuities that is the Cantor set. Okay? So our next question becomes, is the Cantor function Riemann integrable on 0, 1? So in particular, does the Riemann integral from 0 to 1 of the Cantor function of x dx, does this really exist in R? So think about it for a moment, pause the video if you need to, but the answer for this question is yes. And why is that the case? So why is the Cantor function Riemann integrable on 0, 1? Well, the set of discontinuities for the Cantor function is the Cantor set. And the Cantor set is a null set, but it's very important to note that the Cantor set also is an uncountable subset of 0, 1. So before, our examples were just based on null sets that were countable sets, but here we have a null set that's an uncountable set. So it's almost like the irrational numbers, right? So what does that mean? So Riemann integrability doesn't really care about the countability of its set of discontinuities. It only cares about practically how much area those discontinuities cover, right? Which is what null set sort of takes into account. Right? So since the set of discontinuities for the Cantor function is a null set, since the Cantor function is the Cantor set is a null function, then by Lebesgue's integrability criterion, we see that the Cantor function is indeed Riemann integrable on 0, 1. Okay, so even though our Cantor function is discontinuous on an uncountable set, similar to that of our Dirichlet function, that doesn't necessarily mean it's not Riemann integrable, because in this case it indeed is, because the set of discontinuities is a null set, right? So that's actually very, very cool. Okay, now what exactly is the integral from 0 to 1, right? So using some definitions of Riemann integrals, you can show very easily that the integral from 0 to 1 of the Cantor function is actually equal to 0. And you should be able to also show that the integral from 0 to 1 of the Thome function on also 0, 1 is also equal to 0 as well. Okay, so that's actually very, very interesting. And those are some of the things that you definitely should know about null sets and how null sets can be used to help you determine the Riemann integrability of functions. Hope you enjoyed this video, and I'll see you in the next one. Take care.